Hi, my name is Anja Knigge and I work for Kirchhoff. Today I want to talk to you about fiber coupling. So the topic of my talk is perfectly coupled single mode fiber coupling using the laser beam coupler 60 SMS. Let's talk about fiber coupling. First, why fiber coupling? Then coupling into single mode fibers. Then we want to get in detail about the laser beam coupler 60 SMS and its stability. And then finally how to choose the right coupler using the Kirchhoff product configurator. Why fiber couple? Fiber coupling leads to modular, complex, and self-contained setups that are compact, long-term stable, and have an improved laser safety. You also have a defined interface between the laser source and the measurement setup. So how does coupling into single-mode fibers work? Well, first you have a collimated input beam. Then you have a lens with focal length f, and then the beam is focused down onto the fiber in phase. Single-mode fibers are characterized by the numerical aperture, the mode field diameter, and the cutoff wavelength. The numerical aperture describes the angular extent of the beam emerging from the fiber. And the mode field diameter describes the diameter of the Gaussian intensity profile measured at the 1/e squared level. So what is the condition for best possible coupling efficiency? The beam's field distribution at the fiber entrance has to have the best possible match or overlap to the fiber's mode field. If you have the input beam diameter and all the fiber parameters, all coupler parameters are already determined. This is especially true for the laser beam coupler's focal length, because the focal length depends on the beam diameter and the numerical aperture. So usually you have a standard nominal fiber in A given by the manufacturer at the 1 to 5% level. At Kirchhoff, we measure an effective numerical aperture at the 1/e squared level, and we do that for each fiber and for different wavelengths, because as you can see here on the right, the numerical aperture and the mode field diameter are both wavelength dependent. This gives you a much more precise choosing of the focal length. So now we want to talk about the laser beam coupler and its degrees of freedom. First, you have to choose the ideal lens with optimum focal length. We've already discussed that. Then the laser beam coupler needs to be focusable, it needs to provide an angular adjustment, a centering of the optics, it has to have a pre-angle coupler axis for fibers of type FC-APC, and with polarization maintaining fiber, you need to provide an adjustment of the polarization axis to that of the laser. Only then you can achieve high coupling efficiencies of up to 84%. So first, the adjustable focus. The laser beam coupler has an independent focus setting using an eccentric key that is inserted here. With an optimum focus setting, the beam is focused down right on the fiber end phase. As you can see here, for a defocused lens, the laser spot is no longer located on the fiber end phase, and the mode field overlap with the beam is reduced and coupling efficiency is reduced. Then the laser beam coupler needs to provide a centering of the optics. To match the angular orientation of the mode field, the optics of the coupler needs to be centered to the beam. If the optics is not centered correctly, it does not match the fiber's acceptance angle, and the overlap between mode field diameter and spot is no longer ideal, and part of the radiation is not coupled correctly into the fiber. Then the laser beam coupler needs to provide a tilt adjustment. To match the lateral position of the mode field, an angular adjustment is required. Fiber entrance and optics are tilted until the optical axis is aligned to the beam. The laser beam coupler has a tripod tilt adjustment using 3 radially arranged screws and 3 locking screws. An angular misalignment leads to a lateral displacement at the fiber entrance, and this also reduces coupling efficiency. Finally, the laser beam coupler needs to be rotatable, because for polarization maintaining fibers, you have to align the fiber axis to the polarization axis of the laser source. Here you have a cut through a polarization maintaining fiber. You can see the fast and the slow axis. So usually the radiation is coupled into the slow axis. The laser beam coupler can rotate 360 degrees to do that. So now, how stable is the laser beam coupler? What we've done here is we put one laser beam coupler against another laser beam coupler. So we've coupled out and then coupled in again, looked at the relative power, and that while varying the temperature between 15 and 35 degrees Celsius. You can see here this repeated test, and the relative power has a maximum deviation of only 1.5%. We've then repeated this test a few times to show the high reproducibility and pointing stability, and maximum deviation is only 3%. So how do you find the right coupler? You can do that using the Kirchhoff product configurator. You can insert all your coupling parameters here. What I've done here is I've put down wavelength, used with polarization-maintaining fibers, coupling only. You can choose Schäfter and Kirchhoff fibers. This is good because then the effective numerical apertures are already inserted for calculations. You can input your beam diameter, and I've put down I want to use with an FC APC type connector with a p-angle coupling axis. And what then happens is the long list of couplers is narrowed down to these few options that are perfect for your application. You can then select the couplers and compare. All key features are listed and differences are marked in bold. You can also look at the detailed product pages with all the technical data. So where do you find this product configurator? You can find it on www.sukhamburg.com. You can find way more information about fiber coupling there, and please contact us if you have any questions. Thank you for listening.